Let's look at G-GMD.A.1, Activity 6. This is a fun little concept. We do not really have a good, clear idea when we say the area of a circle is pi r squared. We don't have a real good idea where that comes from. Well, this is the attempt to show you where it comes from in a fairly simple manner. There are other ways to do this, but this is a nice way, a geometric, a visual way to help you understand it. It's kind of called the limit argument. In other words, we're going to kind of approach a limit, and this is a nice concept also for the future when we get into higher levels of mathematics. Limits become important. Here's the idea. We're going to dissect, really, like we've done in other shapes, the circle, and we're going to cut it into 4 nice equal pi pieces, and then I'm going to arrange them to form a shape that looks like this. And if I was to ask you what shape does that kind of look like, you might say, I don't know, a parallelogram. And you're right, is that that's the idea of what I'm trying to do, is that there's kind of a parallelogram-like shape in here. And so the area of a circle is kind of, can be approximated by the area of a parallelogram. But there's some bumps out here and stuff, so obviously it's not very accurate. And that's the whole idea. When I cut it into 4 pieces, it's not very accurate. The height would be almost the radius, but the radius of one of these pi pieces, can you see, would go from its old center to here, which is not the actual height of our parallelogram. And the other element is how long are these sides. Now this is the fun thing to figure out. Do you see how it has 2 of the arcs here and 2 here? Well, the entire circle has a circumference of 2 pi r. So half of the bumps are here, half of the arcs, I shouldn't call them bumps, and half are up here. So, you know, that this bottom base is kind of almost like half of the circumference, 2 pi r. And then the height is almost the radius, and if you multiply base times height, you get pi r squared. Which is very cool, but you say, that's not a parallelogram. But what happens if we go back to our circle and cut it in 6 pieces instead of in the 4? And we find that when we do that, all of a sudden things are looking up, because do you see how, like, the arcs, they're just barely stretching past the parallelogram, and that radius is just barely going outside of that guy. So actually it's getting closer to the value by cutting it into smaller pieces. This is still pi r, and this is still r. It isn't a perfect parallelogram yet, but let's go cutting again. Let's cut it out into 8 like this. And when we get to 8, things are starting to look really good now. Well, much better than the others. That radius is almost the right radius, and this I keep writing 2 pi r, but the pi r is pretty close. There's not much kicking outside of that. And so the idea is, what happens if we didn't split it into 4 or 6 or 8? What happens if those pi pieces, those sectors, were cut 100 times? And then it would almost be, it would approximate to be that parallelogram with a base of pi r and with a height of r. In other words, pi r squared. Let's take a look at a cool little example of this on the computer. You'll see what I mean. It's pretty cool.
All right, I want to show you the relationship that I tried to show you on the board, but I'm going to do it here using technology, and this rules compared to what I tried to do. This is a little app made in GeoGebra by Linda Falberg, and so I want to give her the credit for such a beautiful piece of mathematical representation. Let's show you what we're talking about here. First of all, is we see that here are those pieces, right? So we're cut into 4 pieces, 1, 2, 3, 4 of those pieces, and they've kind of sliced this and put it over here just to rectangularize it just a little bit for us. But we can see we're losing some of the area out here. And if we went to a different number of cuts, 6 cuts, you see how 6 fit in there. There's some loss. There's no doubt there's some loss because we're out here. But if we continue to keep going, 8 cuts, 10 cuts, 12 cuts, this is a beautiful piece of work. Notice how that radius length here to here, there it is, it's basically your height. And then this is pi r, or half of the circumference of this guy. And so pi r times r, pi r squared. And if we went all the way out to 36 or whatever, we see we have air here, but as we make our limit towards positive infinity for n here, the number of cuts, man, we sure get that. What a beautiful job. Thank you, Linda. This is great work to visually get the idea of that limit argument. As we cut pieces that become thinner and thinner and thinner, our radius approximates our height, and then half of the circumference approximates this base. Nicely done.